Okay, howdy. So let's get this started off with what a charge is. So we'd like to figure out what charges are. Well, we know what those are. We talked a little bit about that. There's an elementary charge called an electron. Let's write that here, electron. An electron is an elementary particle, and this is basically what causes all the trouble for macroscopic objects. There are other microscopic objects that have charges on them, quarks, for example, but when we're looking at things in electronics, in electricity and magnetism at the macroscopic level, it's always, or almost always, these electrons that are causing the problems. So we're going to look at those, all right? We'll symbolize an electron as a lowercase e, like that, with a little minus sign on top. It has a pair, an antimatter pair called a positron, where you have to put a positive sign, a plus sign, next to that e. Won't use a lot of those because they don't show up very much. They show up in, your brain sometimes. Sometimes you can look at positron emission tomography out of your brain to figure out what's wrong with it. But normally you don't worry about too much antimatter, except the antimatter in your brain. So, and antimatter, when it comes into contact with matter, sort of explodes. So don't worry about that too much. So the charge of the electron is minus what we call it, minus E. So that's our elementary charge. Every charge is a multiple of E in some sense whenever we do this. However, E is tiny. E is 1.609 times 10 to the minus 19. It's supposed to be a 9. Coulombs. Right, and we're dealing, and a normal sort of charging thing is on the microcoulomb level, like 10 to the minus 9, 10 to the minus 6. That's a normal sort of charge. So even the small amount of charge things get in the real world, this is tiny. So we can sort of ignore the fact that this is in lumps. Instead, we can just imagine, unless we want to take things down to 15 or 20 decimal places, we can just imagine that the charge in coulombs is a real number. That makes life easier for us, so we don't always have to count charges. Now, today we'll count charges, but later on we won't count so many charges. We'll just talk about the total charge on any particular object. Now, charge is not, at the macroscopic level, charge is not an intrinsic property of the object. So if we had a weight, right, its mass is sort of an intrinsic property. It sort of tells you how many things are there, and it doesn't change. You have to really break something to change its mass in general. For charge, that's not true. You can add and subtract electrons, and that's something that you do all the time, by walking across a carpet or something, and then you get a shock at the doorknob. That's because you've sort of generated some electrons, on your body by walking across that carpet with your little rubber shoes, with your rubber soles, and that just electrifies your whole body, and zap, you get it. It's always fun. It's the kind of thing you like. So that sort of charging, that triple electric charging, is very, very important. And if I make more advanced sort of videos than this one, we'll talk a little bit about that in those videos. But don't count on it, because I have to get all of these done first, right? So in general, it's however many electrons something adds to it over the number of atoms in it, or the total number of protons in it, right, really, that gives something its charge. So if you were to say take a molecule, right, and it had a whole bunch of electrons on it. So it has these orbitals. We have electrons in the orbitals. Each orbital gets 2 electrons and stuff like that. This is small, so if this guy's filled and this guy's filled and this guy's filled, but it loses this electron, that guy's lost, he has a charge of plus E because he's lost 1 electron. That happens on all of the molecules in your body, all of the molecules everywhere. So what we want to do is we want to have something for an even larger thing than a simple diatomic molecule. We want to look at something bigger than that, say a person or a dog or an electrostatic charge generator like a Van de Graaff generator. So this is our first point, is that the charge on an object is caused by an excess or deficit of electrons possessed by the object. And the question is now, what do I mean by excess or deficit? Well, if I have this molecule here, where I said it had 4 of these electron states, that means there are 4 protons in the molecule. Actually, that's pretty bad. That's sort of like helium, diatomic helium. That doesn't exist. That's sort of bad. All right. So this guy has a deficit of electrons because this electron over here was lost, right? So this electron came over here and was lost. So we have 4 protons minus 3 electrons gives you plus E as the charge. So that is the charge. We call charge Q usually, charge. And I don't know why they decided to choose Q for that. Might have something to do with transliteration of Greek letters. Might also have something to do with, French. You never know. And that's equal to the number of protons minus the number of electrons times this elementary charge E. So again, we have plus E over here. This thing has a charge of positive 1.609 times 10 to the minus 19 coulombs because it lost 1.609 times 10 to the minus 19 coulombs when the balancing electron here disappeared. So it's out of balance. And you know that from chemistry and all that other stuff. You need balance, so balance sort of atoms and things like that. So this guy was the number of protons. This guy here was the number of electrons. And this is your elementary charge that we had up there. There is no macroscopic charge that is not a multiple of that. Now, there are quarks that have, we hopefully talked about this before, there are quarks that have a smaller charge them that have a charge of 1/3 of an electron charge, but they always occur in threes. So since they always occur in threes, they end up always having a charge of those units of 3 always end up having a charge that's integral in E, so that there's always a whole number of E's, which is really creepy. It's very, very creepy, and you should think about that at night. Okay, so that's more or less what we've got here. The example problem that I'll make will have to do with calculating this for a cube of some material, some matter, and I'll get to choose that. And then we'll go on and do part 2, and part 2 will be on where the charges are in the material. All right, so right now we just said, material will have a bunch of charges. Next we'll say, well, where do those charges go? If you have an excess or deficit of a charge, where do they go? That's coming up next. All right? Talk to you soon.